promised you that using the first principle to find the derivative of this function is a lot easier than your teacher made it. You'll have to stick around to see for yourself because we're going to crush this in just a few minutes. Remember, for the classic definition of a derivative using first principle, we're introducing this very small constant h here. So what we want to do now is go back to the original sine of x function, and for the left part of this limit at top, instead of x, anywhere you see x in the function, you're going to put x plus h. And then you're going to subtract it from the original function itself, and we're going to let this value of h get infinitesimally small, where you can kind of think of it as finding the slope at a point for a derivative. So remember, though, that with sine of x plus h, the first thing you want to remember here is we've got a cool trigonometric property we can use for sine of something plus something, where that expands out to a sum of terms here. That becomes sine of x times cosine of h plus sine of h times cosine of x minus the original sine of x all over h. And maybe many of you got stuck here and your teacher didn't do a great job, and that's okay. We're going to work through it together. Remember now, by inspection here, I want you to remember something really important, right? The first thing is you want to look at what terms are in common when you add and subtract all these different trig functions. Notice that we actually have sine of x at the front and at the back. So I'm going to go ahead and just factor that out right now and rewrite the expression so that sine of x can now be factored out, giving us cosine of h minus 1 plus sine of h times cosine of x all over h. And now you might be wondering, what do I do here? I've got two different variables and I've been stuck, Ninja Dave. So remember, here's the cool, important thing you need to remember here. You're taking a limit as h approaches 0. So as h is ever so changing, remember that x is actually fixed. What that means then is that any term that has an x in it, we can basically bring it outside of the limit. But before I do that, the first thing I want to do is actually break this up as a sum of limits. We can safely break up this fraction here because it's going to be easier to work with smaller chunks. So by doing so, I'm going to rewrite this expression here where I've grouped sine of x times cosine of h minus 1 all over h as its own separate limit. And then the remaining part, this sine of h times cosine of x all over h, will be the limit to the right. So I can then work with each one of them individually. And this is now where I'm going to bring out the x terms. So sine of x can be brought out of a limit when only h is changing. And then similarly, I'm going to bring out the cosine of x term on the right. And now what I can do is some really cool stuff. So when I work with this expression now, I want you to notice something really important here. On the right-hand side, we can really simplify things because the limit as h approaches 0 of sine of h all over h, you probably have seen this very famous squeeze limit theorem limit. We know that this is 1. It doesn't matter that we're calling it an h here or an x. That's a very simple simplification we can make here, where that term times cosine of x will just simplify to cosine of x. So we know intuitively, right, that the derivative of sine of x should be cosine of x. So our goal now is this expression on the left. What can we do to prove that it's going to go to 0? Because then 0 plus cosine of x will give us our final answer, right? And before I show you that, if you haven't already, you want to become a ninja today, be sure to ninja kick that subscribe button for more tips and pick up some cool swag you can wear in the dojo in the description below. So now what we got to do is, okay, with this expression here, I'm not going to worry about the sine of x part. I'm going to just work with the limit as h approaches 0 of cosine of h minus 1 all over h. So we want to see what this turns out being. And you may already know this from squeeze limit theorem, and that's okay. You can skip forward if you want. But ultimately, for those who don't know this proof, in case you may have to be showing this proof on an exam, what you want to first do is, we know by inspection, if we just plug in 0, we're going to get 1 minus 1 on the numerator, which will be 0, and the denominator will be 0 as well. So we're going to have an indeterminate form, 0 over 0. But ultimately, what we're going to do is multiply both the top and the bottom by cosine of h plus 1 all over cosine of h plus 1. And our goal here is to transform this problem in such a way where we can use the famous trig identity that sine squared of x plus cosine squared of x equals 1 to see if we can rewrite this in terms of sine. And the idea with that is then we could hopefully use a squeeze limit theorem. So moving ahead, when you multiply cosine of h minus 1 times cosine of h plus 1, essentially that's an easy FOIL method to give us cosine squared of h minus 1. And then for the denominator, we've introduced this cosine of h plus 1. Okay, so moving forward now, I can't substitute in for sine squared of h above because that would require 1 minus cosine squared of h. But what we can do actually to manipulate this to allow it is I can multiply both the top and the bottom by a -1. So I'm going to do that here. And that's going to allow me to rewrite this limit expression as 1 minus cosine squared of h on the top. And then the bottom will just have this -1 factor in front of h. And then we can use our trig substitution method there, because if sine squared of x plus cosine squared of x equals 1, which I'm calling it h here, then if you were to solve that trig identity for sine squared of h, you would just subtract cosine squared of h on both sides. So we can safely put in sine squared of h here. And now what I want you to remember is that when you have a limit of a fraction that consists of products, it's no different than multiplying their separate limits together, right? So we can actually decompose this fraction as a product of terms. So sine squared of h has two sine terms, right? I can rewrite this now as a product of negative sine of h times sine of h over h times 1 over cosine of h plus 1. And the reason why I'm doing this is now if I make this a product of separate limits that are easy to work with, check this out. The limit as h approaches 0 of negative sine of h is simple. You can safely plug in 0 there without dividing by 0, and you'll just get 0. Now, the second middle limit, we already know from above. We use that up there as well. That's the famous squeeze limit theorem. We know that one is 1. And then finally, for the rightmost limit, when you plug in 0 on the bottom, you're going to have 1 plus 1 on the denominator, and the numerator will be a 1, giving you 1/2. And check this out. When you multiply 0 times 1 times 1/2, this all goes to 0 and gives us this final answer.